Hello world and hello maths fans. Today we are talking about functions. Mathematically, a function is simply a process that is applied to a collection of inputs to generate some outputs, which means functions are everywhere in the real world. Searching through a data set is a function, and as is anything that changes over time. In today's session, we will begin with defining variables and equations. We'll then look at how we can translate word puzzles into variables and equations to help us solve them via the tools of mathematics. We'll then get onto the formal definition of a function, and we'll look at associated terminology such as domain, codomain, and image. We'll discuss backwards functions, or more correctly, inverse functions, which take us from the outputs back to the inputs, and we'll see that they only exist under very special circumstances. We'll end with two particular types of function: the counting functions, enabling us to understand the size of infinite sets, and my personal favorite, the Pokemon catch function. Let's go catch them all. Yeah, I'm happy.
I don't think you need a second take.
Sometimes I get it right first time. let's talk about my favorite function, the Pokemon catch function. In case you hadn't realized, I am a little bit of a fan of Pokemon. Now, there are two main reasons why this is my favorite function. So first of all, it's because I grew up playing the games. And for those of you who are perhaps unfamiliar with the world of Pokemon, just imagine our world, but instead of being inhabited by animals, it's inhabited by much cuter, funkier creatures, such as those shown on the table. You possibly will recognize Pikachu being the main mascot of the whole franchise. Now, as you explore this world, you have interactions with these creatures. They pop up, and you have a chance to try and catch those creatures. And in fact, one of the first mottos of the game was "Gotta catch 'em all," as you were challenged to see if you could collect or catch all 150 different Pokemon. Now, it's the catch mechanics, the actual process of catching the Pokemon that happens in the game, which is explained through the catch formula. And this is the reason why it's my second. Let's talk about my favorite function, the Pokemon catch function. Now, there are two reasons this is my favorite. First of all, I'm a little bit of a fan of Pokemon. Possibly the shirt and the tattoos may have given that one away. But second of all, the function we're going to explore is actually the original function that is hard-coded into the first Pokemon games. So this is a real piece of mathematics, of computer science that was hard-coded into those famous Game Boy games. Now, for those of you who might be unfamiliar with the world of Pokemon, imagine our world, but instead of the animals, creatures that we're used to seeing outside, the world is inhabited by Pokemon. Now, Pokemon are basically animals, at least at the beginning, but they are a little bit cuter and a little bit fuzzier, as you can see from these examples on stage. You also probably recognize Pikachu being one of the most famous images anywhere in the world and the mascot of the Pokemon franchise. Now, when you're playing the game, you're roaming around, and occasionally you will bump into one of these wild Pokemon. And you're given a task at the beginning of the game by Professor Oak, who says, can you catch all 150 Pokemon? The original motto was, in fact, gotta catch them all. So how does that catch work? So you bump into a Pokemon, it appears in front of you, you enter the battle scene. And during the battle, you can attack this creature, but eventually you reach a point where you select an item. And you select an item, and that item is one of these Pokeballs. So once you select the item, the game then does this for you, throws the Pokeball at your creature. And then there's some wiggling and there's some suspense. Sometimes it says, congratulations, the Pokemon was caught. Other times it says, oh no, the Pokemon broke free. Now, what is determining whether or not you succeed or fail is the Pokemon catch function. And this is what we're going to break down over here on the slides. So the way this works is I'm in a battle with a wild Pokemon. I've decided I want to try and catch it. Now what the game does is it selects a random integer. And at this stage, think of it, we don't really have any control over this random number. Imagine drawing counters out of a bag or pulling a name or a number from a hat. So we draw a random integer, positive integer. If that number, which we're going to label n, if that is smaller, strictly less than, some fixed number c, then we have success. Now, n is what we would refer to as a multivariable function. There are actually several inputs that determine the final value of n that is then used for this comparison. And we will get to those in a moment. But c, as a variable, is fixed by the Pokemon that you're trying to catch. So depending on the Pokemon in front of you, each one will have a unique or an individual catch rate formula, catch rate number. Now, if we look at some examples, a very common Pokemon, possibly the most common Pokemon in the game, is Pidgey. It's basically a pigeon. And it has a catch rate of 255. Now, it turns out this is actually the maximum catch rate, which is telling you that Pidgey is one of the easiest Pokemon to catch in the game. Those of you with a background in coding or programming may know why we're using 255 there. I'll let you think about that one. So Pidgey, right, big number, so there's a lot of numbers we can get that are smaller than 255. But a Pokemon that's really difficult to catch, let's say a legendary Pokemon, which you only meet right at the very end of the game, something like Zapdos, my favorite legendary, Zapdos has a catch rate of 3. So the only integers smaller than 3, greater than or equal to 0, are 0, 1, and 2. So as we can see, there are a very few selections for the value of n that mean we catch Zapdos, which is why Zapdos or other legendaries are very difficult to catch. But we can do things when we play the game. Again, those of you watching this who have experience with Pokemon will be thinking, well, there's certain things we can do to try and help us catch the creature. Now, we're going to focus on two of those things because both of them affect the value n. So again, c is fixed. We can't control that, fixed by the Pokemon in front of us, but n we have control over. Now, that input is determined, first of all, by our ball choice. So the Pokeball that we're using to throw at our creature, the item we select, they actually have different ranges from which n is drawn from. So at the very beginning of the game, we have the Pokeball, so the red one here on the table. And if you're using a Pokeball, the basic one, your integer n is drawn randomly from 0 up to 255, so across all 256 possible values. If you then progress through the game, you are then told, well, try a Great Ball. It's stronger, it's better at catching Pokemon. The game, of course, doesn't reveal these numbers, right? This is hidden in the code. But what we can see about the Great Ball is now our random number, n, is drawn from a smaller range. So rather than going all the way up to 255, if we use the blue one, the Great Ball, we only go from 0 to 200. So we can see that using the Great Ball means there's a higher chance that we get a small number. And remember, small numbers are what give us success, regardless of the value of c. So then if we go even further into the game and we get the Ultra Ball, the one you get towards the end, the Ultra Ball is, again, even stronger. So the Ultra Ball, we're going to expect the range to shrink following that pattern, and that's exactly what happens. So now our integer n is drawn from 0 to 150 when using the yellow Ultra Ball. So here we can very explicitly see in the maths and in the function just how using these stronger Pokeballs is actually affecting our chances of success. Now, the second thing that's going to affect n, because as I said, it's a multi-step function or multivariable function. Lots of things are feeding into this particular function. The second thing is going to be the status of our Pokemon. So during the battle, we can use certain moves, creatively called sleep powder, for example, that puts the Pokemon to sleep, or poison powder that poisons the Pokemon you're trying to catch. And these changes in the status, they actually will subtract a constant value from the random number n, which is more confusing which sounds more confusing than it is. Where should I go? The second input or variable that we can control when trying to catch a Pokemon is going to be its status. So during the battle, when we're trying to catch the creature, we might first use some moves. And those moves, for example, Sleep Powder or Poison Powder, they actually change the status of the Pokemon that we're trying to catch. And those changes in status are going to affect our number n. And the way this works is, depending on the status, we just subtract a constant value from n. So if the Pokemon is asleep or if it's frozen, then whatever number n comes out, so we draw our random number, then we take away 25. So as we can see, this is good, because remember, we want n to be as small as possible. So taking away 25 from n is going to help us. And if the Pokemon is burned, paralyzed, or poisoned, we take away 12. So about half as helpful, but still definitely helping us out to get smaller n, which means we are more likely to have a success. Finally, if the Pokemon has no status condition, this modifier is set to 0, and nothing happens. N is exactly the number that is selected. And that is pretty much it. So again, those of you with experience of playing Pokemon might now be wondering, well, what happens if we lower their health and various other things? So that does have an impact, but that actually feeds into the second part of the catch function. And here today, we are just going to focus on stage 1, and we're going to say that it's a success provided our number n is smaller than that catch rate. So now we know how it all works. It would be great if I had a volunteer somewhere to come and catch a Pokemon. Now, fortunately, I know just the person. Please welcome Colton Ogden to the stage. Woo! Okay.
Hey,
How we
Thanks
doing?
for having me. I can't think of a better math topic to talk about within
I
Pokemon.
knew you were the person for this. Okay, so Colton, you've heard how to catch a Pokemon.
Yes.
Which Pokemon would you like to catch?
You know, Pikachu and Eevee, both legends, in the franchise, of course. But I will say I do have a soft spot for Gen 2. So I think I'm going to go with Phanpy, actually.
Okay, so Phanpy, the cute little blue elephant over here. Okay, there we go. Right, so you want to try and catch Phanpy. Now, if we remember, the key thing when you're determining which Pokemon you're trying to catch is you need to know its catch rate. So Phanpy has a catch rate of 120.
Okay.
So not bad, right? It's not as low.
In the middle.
It's kind of in the middle. It's a good choice, right, compared to the others, right? Eevee is 45 and Pikachu is 190. Okay. So you've chosen wisely, I would say there. Okay, now, if I let you have free reign of choice of Pokeball, which one is going to help you out?
Well, I'd have the best chance with the Ultra Ball, but I got to say, where's the Master Ball? I heard there's a Master Ball.
I knew this question was coming. So, very good point. So the Master Ball in the game, you get one of a kind, and it is guaranteed to catch the Pokemon. And so within the function, within the Pokemon catch function, it basically says, if using Master Ball, Pokemon equals caught. Right, so it's not a fun one for us to demonstrate and do some maths with.
Fair.
But a very valid point, right? Ideally, we'd use the Master Ball. But given you can't use the Master Ball, you said the Ultra one.
Ultra one sounds pretty compelling.
Yeah, it's going to give us the shortest range. But that's going to be too easy. So what I'm going to do, I'm not going to let you freely pick your Pokeball. So what we're going to do instead is we're going to put the 3 of them in this bag.
Okay.
And you're going to draw one at random.
Okay, a little bit of randomness.
Now, I will just pre-warn you that the balls all feel the same inside the bag. So you cannot, I know how otherwise you'd
Can't try and guess which one it is.
Exactly.
All right.
So which one have we got?
This one.
Oh,
Ooh,
he's
I
got the
lucked
Ultra
out.
Ball. Okay, so if you remember from our lesson earlier, what's that going to mean for our numbers?
Well, it's going to be the range of number that we are going to draw is going to be between 0 and 150 with this one.
Exactly. So we've got the shortest possible range, and we only need to get smaller than 120. So I feel like you're in a good position already.
Yeah, if luck holds out.
However, yeah, you're right. It's probability in it. However, we're also going to determine the status of your creature.
Okay.
I'm going to do this with this inflatable dice. So if we look at the screen and the status conditions,
Okay.
so we'll say that the ones you want are sleep and frozen.
Yep, minus
Biggest
25.
modifiers. That will be 6 and 5.
Okay.
Then 4, 3, 2, 4, 3, 2 will be burn, paralyze, poison, and a 1 is going to be no status.
All right. Sounds good.
So give that one a roll.
Let's see what we get. Ooh, suspense.
It's
Got
a 6. Okay. So, right, so we've got the range is going to be 0 to 150.
Okay.
Whatever number you get, you're going to take away 25
Okay.
because your Pokemon is asleep.
Okay.
And you need to get, to successfully catch Vampy, you need to get a number strictly less than 120.
Okay.
So what is the maximum number you could get, taking into account all of our modifiers?
So 119 would be 1 less than 120.
Yeah,
And then we're going to modify our result at the end, right?
we are. Yeah, because of the status.
So what would we end up with at the very end then?
So you need to end up with 119. So if you were to draw something like 140, maybe even a bit higher, and then you take away that 25,
I see.
it's going to take you below the 119.
Right, okay. So we're going to be at like 115, 113 in that case-ish.
It's going to be 144
Okay.
would be the largest number that you could get.
I see. Okay, that makes sense.
So 144, it's tricky to kind of do all this. Like, this is why the Game Boy does it for us, right?
Yeah, exactly.
It does keep track of all of these things. So if we get 144, we would then use the modifier of minus 25,
Okay.
which would take us down to 119, which would then successfully be a number less than Vampy's catch rate of 120.
All right. Sounds
So-
good. Let's roll for it.
You drew the Ultra Ball, which means I have this yellow bag, color coordinated, which contains 151 counters that I have written the digits 0 through to 150
Oh, man.
on. So you're going to live action, draw a random number, and again, from 0 to 150, if you get 144 or smaller,
Okay.
we're going to successfully catch Vampy. So I feel like the odds are in your favor, but
Odds
you
are in my
never
favor.
know.
All right. Let's see what we get. 106.
106 is a success. So Colton, please take Vampy with you. You have successfully caught the cute little blue elephant. think of a number. I would recommend picking something with 1 or 2 digits, but feel free to pick any number you want. Add 7. So take your original number, add 7 to it. Keep that number in your head. Double it. So again, the number you just had in your head, multiply it by 2, double it, keep the new number in your head. Subtract 10. Halve it. Subtract the original number you started with. Now there should be a final answer in your head. Here's the magic. I guarantee the answer in your head right now is the number 2. Magic. Not really, it's just maths. Let's have a look at what was happening in that trick. So we are going to represent the steps in my magic trick using a table. So if we begin to fill in this table, I will put the instructions I gave you in the first column, and then we will track what is happening using an equation. Now, the first thing I asked you all to do was to think of a number. And since you were thinking of your own number, I do not know what that is. So it's a variable, it can vary, it can change. So here I'm going to represent that with the variable x. Now the first step, having thought of your number, I then asked you to add 7. So if we started with some number x, and now I've asked you to add 7, then what we're left with is going to be written as x plus 7. And again, this is true no matter what x you picked at the beginning. The next step was to double it. Now there's a little bit more work here, but what that means is to take the previous line, our previous equation, x plus 7, and multiply the whole thing by 2. So we have to be careful when multiplying out those brackets, but we're going to get 2 lots of x plus 2 lots of 7. So both terms have to be doubled, so we're left with 2x plus 14. The next step was to subtract 10. So we've got 2x plus 14, subtract 10 is going to leave us with 2x plus 4. So notice the x value hasn't changed here, the x part of the equation is unchanged, but the 14 has gone down to 4. Then I asked you to halve it. So this means to divide the whole equation by 2 or to multiply the whole equation by a half. Doing either of those things, the 2x becomes an x, and the 4, when halved, gives you a 2. So now we're at x plus 2. And the final step, and you might have noticed what's happening here, was to subtract your original number. Now we represented your number with x, so when we now take away x from x plus 2, we get back 2. Now, of course, I did not even have to do any of this in my head, because I knew the maths, I knew the equations that were underpinning the magic trick. So all I had to do was just pretend that I was doing magic, because the answer, no matter what x you pick, we can see here the answer is always going to be 2. Now this is a really nice example of how we can use equations and variables to translate a complicated problem. There were lots of steps, lots of things happening, but using the tools of maths, we were able to write it in a much more understandable manner and also figure out what the solution was going to be. movie magic that is about to happen. So the next period of time might not make much sense to you, but I promise you that the final video, everything will make sense.
Sorry, Tom, can you say that one more time? We actually had the audio down over here.
Okay, no worries. Yeah, but that was fine. That was all I need to say.
That was great. Can you
Okay.
say it one more time?
Yeah.
Go ahead.
Okay, hello people watching the live stream. So we're going to get a true behind the scenes moment here as we are going to be filming several things out of phase for a very fun and complicated demo about functions. So the initial part might not make much sense, so hopefully you can just enjoy the behind the scenes magic, but I assure you that when we put all of this together for the final video, it will be a beautiful demo showing you how functions work. ta-da! My function portal is now on stage. So at the moment, I'm just going to check. Yep, it is set to channel 1. So in order to try and determine what particular function is related to channel 1, I'm going to throw a few items through and let's see what happens. So first of all, let's try the dice. So again, I have no idea what channel 1 could be. It could be any of the specified functions in the instructions. So let's throw this through and see what happens. Okay, so I've thrown in 1 die and I have got 2 dice coming out the other side. So looking at our list of options, it feels to me like channel 1 must be the duplicate function. 1 single input has been copied and we have 2 coming out the other side. Okay, so mystery of channel 1 solved. Let's change this now to channel 2. Okay, so again, I'm going to toss in one of these items, see what happens. So it could either be the mystery function, enlargement, or it could change color. What do I think for this one? I'm going to go with a basketball. Let's see what happens with this one, shall we? Okay, so again, this is to determine what type of function we've got on channel 2. Okay, so a big basketball has come out the other side with a small basketball having initially gone in. So we're seeing there a change in size, which again, if we look at our list, that means that must be the enlarge function. Small item went in, copy, but much bigger has come out the other side of my function portal. All right, we're nearly there, so let's change it now to channel 3. There we go. So this could either be the mystery function, which I have no idea what that's going to do, or possibly the color change. And for this one, I think I'm going to try the rope. So let's see. It may change color, or it could do something completely unspecified. But let's see what's going to happen. What is our third function on channel 3? OK, so it's changed color. So we've gone from a green rope to a blue rope, as you can see. So therefore, channel 3 must be the change color function. So we can see there an example of a non-mathematical function. So the first one was duplicating, doubling in a way. We saw that channel 2 was enlarging, which again is a mathematical process. And here we just got a color change. So it's a nice example there of a non-mathematical function that is occurring, which just leaves the mystery. So let's, of course, it's channel 4, the last one. Let's change it to channel 4. Now, I actually have no idea what this one's going to do. I've got a couple of items left, so let's pop those in and see what happens, right? See if we can work out what function is on channel 4. So first of all, lovely rubber duck, very famous rubber duck. So let's throw this in and see what happens. OK, so the duck has gone in, and a banana has come out the other side. So it's definitely not changing color, right? We can rule that one out. We've sort of changed item, haven't we? But we've definitely not changed color, yellow to yellow. It's produced a fruit. So handily, actually, I've got an apple here, haven't I? So maybe my hypothesis at this point could be that our function turns any item you put in into a fruit. Let's see what happens if I put in a fruit itself to the function in channel 4. All right. And we've got another banana. OK, so there goes that hypothesis. It's still a fruit, but I put in a yellow duck and got a yellow banana. I put in a fruit in the form of an apple and got a banana. Maybe it's literally the banana function, the lesser known banana function. But I am, unfortunately, I'm out of items. And I do feel like I want to test this hypothesis. So I guess I'm going to have to just test myself at this point. Wish me luck. A function is simply a specified process that is applied to a collection or set of inputs to produce a set of outputs. Forgot what I was going to say next, sorry. Back it up, OK. I was saying what a function is. A function is a specified process that is applied to some inputs to produce some outputs according to that process. Most of the time, functions are referred to as function machines in the sense that something is fed into the machine and then an output is produced. However, I've gone a little bit overboard and I've got myself a function portal. It is going to behave in the same way. We will feed in some inputs, but they will go through our magic portal and produce some outputs, just like a function. However, there is a slight issue with my function portal in that it has 4 settings, and I'm not actually sure which channel or which setting corresponds to which specific function. Now, fortunately, I do have a list of the potential functions that the portal supposedly will represent or will complete. So if we have channel 1, 2, 3, 4 are the 4 possible settings, and we're going to try and work out, through testing the portal, can we match up the channel with one of the functions. Now, you'll notice 3 of them are specified. The instructions tell me at least one of the channels is going to enlarge something, one of them is going to change color, one will duplicate. But the last one, we don't actually know what that function is. And again, these channels are not necessarily lined up with the order as written on the board. We're going to have to decide how to join those up. But in order to do that, I'm going to need to actually test out the physical function portal. Now, as I mentioned, fortunately, this thing really is magic. Watch. don't worry, I haven't really turned into a banana. Let's take stock of everything we've just learned about functions. So remember, a function is simply a process, a specified process or rule that is applied to a set of inputs to produce outputs. Now that set of inputs, where the function takes those elements from, is called the domain. So you begin in the domain before then passing through the function. And the set of outputs, the set containing the outputs, is called the codomain. So inputs come from the domain, pass through the function, and go into the codomain. Now the specific values produced by the function are often written as the image of f, where we write here im of f. So in our final example, with the magic of turning everything into a banana, we would say our domain there was the set of items on stage. That was where I was drawing those inputs from. Then it passed through the function being turn into banana, and then we would say the codomain was the collection of objects that were coming out, but specifically for the banana function, the image was just banana, because no matter what input we put in, we always got the banana coming out the other side. Now visually, we can show this with a diagram like the one on screen. So if we have a function f and we have a domain x and it's mapping into the codomain y, then we use this arrow notation to show that movement between those two sets. And we can show this on a diagram as shown below. So we've got f here with this red arrow showing the function is passing us from one set to the other, so the domain and the inputs into the codomain and the outputs. And there's also an important piece of notation in this diagram, which is if we have an element lowercase x which has gone into the function, then specifically the image of that value, the output from that input, we often write as f of x. So that's saying x has gone in, f has been applied, so what we're left with is exactly f applied to x, or f of x. So let's go over now and look at some mathematical examples on the board. And these ones will not feature bananas, unfortunately. So let's look at the following function. So suppose I have a function, I'll call this f1, and this is going to map between the domain 1, 2, 3. So that's a set of 3 objects, and it's going to map into the codomain, which again is our collection of outputs, 3, 4, 5. And let's suppose now that this function is given such that if I have an input x, so again x is coming from that set 1, 2, 3, then we say f1 of x is just x plus 2. So to just make that really clear, we've got here the domain where we start from, take our inputs 1, 2, and 3, and they are mapping into the codomain over here, which is 3, 4, and 5. OK, let's look at a second example to make sure this is really clear. So f2 of function, let's have this one go between, I think we're going to do the same domain. So this is still 1, 2, 3. But this time, it's going to map into a different codomain. So this time, we're going to get 1, 4, and 9. Now, I'm just going to pause for a moment and let you have a think to yourself what this function could be. So we've got 1, 2, and 3 mapping or outputting 1, 4, and 9. So if we think about that for a little moment, you hopefully will realize that what we're doing here is taking our input x and we're squaring that value. So we're multiplying it by itself, which we write as x squared. So 1 times 1 gives us 1, 2 times 2 gives us 2, and 3 times 3 gives us the 9. Now, we can also have other functions where the image is not the whole of the codomain. So in those first 2 examples, all of our outputs, all of the image, were the same as the whole set that was coming out. So if I slightly modify the one that we just saw. So let's call this function 3, and I'm going to give it a new name because I'm changing the codomain, so that actually changes the function. The function is defined through its domain, what it does, and its codomain, and that's important to remember. So if I do the same domain, so we're starting with the same 3 elements, but now we're going to say, well, the codomain is now Z, so or Z, the collection of integers. So we're mapping from 1, 2, 3 into the collection of integers. Now, again, we can keep the same function, so we can say f3 of x is still squaring, but again, this is a different function because it has a different codomain. However, in this situation, the image of f3, again, those explicit values that come out of the function, is in fact going to be the same as we had before. So 1 times 1 still gives you 1, 2 squared gives you 4, and 3 squared is giving you 9. So this is the image, which is a subset, it's a smaller part of the codomain, where the codomain is all of the integers. Now we're going to look at one final example of a completely different function, and possibly one you may not have seen before, but it is one of my favorite functions. And this function is going to be called the ceiling function. So the ceiling function maps from the real numbers, so now we're allowing numbers with decimal expansions, and it's going to map from the real numbers into the integers. And the way that this is going to work is when applied to a number with a decimal place. So let's take a very famous number with a decimal place, 3.14. So if I apply my ceiling function to 3.14, then what it does is it takes the next biggest integer. So you kind of take the number that we have and go up. You always round up. So it's not a rounding function. You're always going up with the ceiling function to the next integer. So if we're at 3.14, we've gone past 3, so we have to go up to 4. So applying the ceiling function here, this will actually output 4. And the way that we often write the ceiling function, I don't want to write f, the way that we write the ceiling function is using these square brackets. So if I have 3.14, and what we do is we write a square bracket, but only with the top section. It's telling us to go up to that ceiling. So 3.14 goes to 4. And similarly, as you may have guessed, we have the floor function, which is going to go down. So just to spell that out for us, so the floor function, it's very similar notation. So if we apply that to 3.14, then that's telling us to round down to the nearest integer. Or you can also think of it for the floor function, just keep that first part of the number. So that would give you 3. And a subtle but important point for both the ceiling and the floor function, if we input an integer, so I'll just really write it out. So if I input the number 2 into the floor function, we already have an integer. So it just outputs the same value that has gone in. So to summarize, we've seen there a whole range of different functions, both mathematical and very much non-mathematical, but they all fulfill this fundamental definition of being a function, which is inputs, something happens, something specified happens, and we get outputs. Equations and variables are the tools that we use to translate a problem, complex problem in the real world, into the language of mathematics, so then we can apply the tools of mathematics to try and find a solution. And they can be very helpful in doing this. So I'm going to share with you some famous word puzzles and look at how we translate the We can use equations and variables to translate complex real-world problems into mathematics, and then hopefully use the tools of maths to solve the original problem. And one of the first examples we see of this technique is with word puzzles. So I'm going to share with you some famous word puzzles, and we're going to look at how we can translate them into mathematics to find a solution. But along the way, I'm also going to point out some of the common misconceptions and some of the common errors that can be made with this translation, so you all know what to look out for so you do not make any of those mistakes. So let's dive into our first problem. Write an equation that expresses the following statement. And the statement is, there are 6 times as many students as professors. We will use s as our variable to represent the number of students and p for the number of professors. So looking through this statement, if we think about how it is written, there are 6 times as many students. So 6, and then we've got students, which we know to represent with s. And then we've got professors, 6 times as many students as professors. So perhaps our first thought here might be to say, well, it goes 6, then s, then p. We want those to be equal. So maybe it's 6s is equal to p. Now just think about that for a moment. Because if we now substitute in a value, so let's suppose I have a single student, 1 student. If s is equal to 1, that says for that 1 student, I've got 6 professors. So it's actually the wrong way round. So the correct equation is s is equal to 6p. Now this is a very, very easy mistake to make because of how the problem is written. And it demonstrates there the importance of once you have an equation, you should always substitute in some simple values to see if it makes sense. Because now, if we input s is equal to 1, then we can say, it's not s is equal to 1. Can I just go from that bit where I say, so now if we, yeah, OK. So now if we input p is equal to 1, for example, there's 1 professor, we see that s is equal to 6, which makes sense. 1 professor, 6 students, sounds quite nice. All right, so that was our first example. Now let's look at a second one. Lucy bought 6 ducks for $12. And the question is, how much does a duck cost? So to solve this, we are going to begin by writing an equation. We're going to need to define our own variable, as one is not given to us in the problem, and then perhaps we have to solve that equation to get the solution. Now I imagine most of you watching have an idea of what the solution should be, but let's just write out those steps and be very clear about what's happening. So 6 ducks for $12. So let's say 6d is equal to 12. So again, that's capturing that information that we have 6 ducks. And then we divide both sides by 6. So dividing 6 by 6 gives us 1. 12 divided by 6 gives us 2. So the answer is d equals 2. How much does 1 duck cost? $2, which of course is the correct answer. But there's a really interesting question here, and this is a really important concept and something you should really be aware of when working with any mathematical equation, which is, what does the variable d represent? Now, hopefully you had your own idea when I wrote down d. You may have read out loud or said out loud what D was representing. But let's just think carefully about exactly what D is representing in this situation. So I'm just going to go over to the surface, because we're going to look at the units that are present here in the problem. So we have the equation. It's 6, and then we're told that Lucy is buying 6 ducks, and then we have D, and then we have the $12. So what we've got is we've got 6 ducks as our units. So I'm going to write that in a square bracket, which is a common notation when you have a unit. So it's 6 ducks multiplied by D somethings. So we don't know the units of D, and we're saying that that is equal to $12. So actually, to be consistent, I should write that as 12 brackets dollars. Okay, so I haven't written anything different to that original equation, 6D equals 12. I've just added units in square brackets. Because now if we can carefully work through and see what units D has. So what I mean by that is if we divide both sides by 6 ducks, remembering to take the units across, we get 12 over 6, so we get 2. And then the units we're left with are dollars divided by ducks. So in that initial statement or initial equation that I've written down to begin the problem, D was not the number of ducks. And it feels like it should be, but D importantly was not. D was representing the cost per duck, which is why we were allowed to get to that conclusion when we saw that D was equal to 2. Now this might feel a little bit like over the top, but this is really important to get the units and to get what a variable represents clear, because once you start getting to more advanced problems and combining variables, you can very easily lose track of what those variables actually represent. Okay, so I've got one more puzzle for us to think about, and this one is related to bikes and trikes. So at a bike shop, they are selling B bikes. So B is an unknown number. Now a bike, hopefully we're all aware, has 2 wheels. They're also selling trikes, and they have some currently unknown number T of trikes, and a trike or a tricycle has 3 wheels. Less common than the bike, but they do exist. So 2 wheels on a bike, 3 wheels on a trike. And again, we want to write down an equation, but this time the equation is going to tell us there are a total of 100 wheels in the shop. So we've got B for bikes, T for trikes, total 100. You know, maybe the equation is B plus T equals 100. Perfectly reasonable thing to begin writing down. But let's just think about this carefully for a moment. So this is saying the number of bikes plus the number of trikes equals 100. There isn't really anything to do with wheels. And we can see this because if I add 1, so if I add 1 to the number of bikes and I add 1 to the number of trikes, both of those two things do the same to the total, right? They're both just adding 1 to the total, which is wrong because this is meant to represent the number of wheels. So what we're missing here is the fact that a bike actually contributes 2 to the total, whereas the trike is contributing 3. So we actually need those coefficients in our equation. So now if I increase B by 1, so if B goes up by 1, then we're going to actually add 2 to the total because of that 2. And similarly, for each increase in T, we're going to add 3 to the total. So this is, in fact, our correct equation. Now, as a final additional problem, can we find a solution to this equation? So we want to know how many bikes and how many trikes, but under the specific condition that we want the number of bikes to be the same as the number of trikes. Now, I encourage you to have a think about this, but the best way to do it is going to actually be by writing out a second equation using the new information. So the new information has been presented in words. So we want to translate that also into an equation, and as we'll see in a moment, that's going to help us to solve the problem. So to just write out where we are at, we've got the original equation, which tells us that 2b plus 3t has to be 100. And then we've been given this new piece of information which says that the number of bikes, which remember is represented by b, we need to know what that variable is, it's the number of bikes, is equal to the number of trikes, which is t. So we now know that b is equal to t, and once we write it in this form, it's now much simpler to understand the problem. It felt quite complex with the words and the statements, but once we've got it as an equation, it's much easier to solve. So if b and t are the same, what that means is I can replace one of them in that first equation. So instead of having 2b plus 3t, it's just the same as 2b plus 3b. So replace that t with a b. So now I've got 5b is equal to 100, adding them together. So b is, of course, 100 divided by 5, which gives us the solution 20. And of course, we know that the number of trikes is the same. So 20 bikes and 20 trikes would give us a solution to that two-part problem. And again, that's a really nice point to kind of sum up what we've seen here, which is the usefulness of variables, equations, in terms of translating these complex problems into something we can solve, but also at the same time making sure that we are very careful about what we are defining our variables to be. And I would always say, do a sanity check, sub in a couple of values to make sure it makes sense. If a function takes us from a set of inputs to a set of outputs, applying some process, then a natural question to ask is, how do we go backwards? So what if I know the outputs and I want to go backwards and see which input that value came from? Now this process has a name and it's called the inverse function. So let's get into the details. So an inverse function, written as f minus 1, telling us that it's related to f but traveling in the opposite direction. It maps from our set of outputs, which remember we call the codomain, back to the inputs, recall are called the domain. Now, here is a diagram demonstrating what is happening. So a traditional function, forwards function, goes from x to y. So our inverse is taking us from the set of outputs, from the codomain, back across to our set of inputs, back across to our domain. And we can see very explicitly now why we write this as f minus 1, because it's telling us to undo the f that is here to get back to that x. So let's head over to the board and have a look at some examples of actual inverse functions. Now, based on the functions that we have looked at previously, one example we could do might be the function f1 going forwards, so from 1, 2, 3 as our domain, mapping into, let's say, 3, 4, 5. Now, for this function, which I've labeled f1, then if we wanted to think about, well, what does it do first, that would help, then f1 of x is x plus 2. Should be careful to specify exactly what the function is doing. So we're adding 2 to those numbers. So to go backwards, again, if you spell it out in this way, it feels almost obvious or intuitive, let's say, that you would just subtract 2. And that's exactly what the inverse function is going to do. So here, we would say, well, the inverse of this function, so if we input a value into the inverse, so we put an x into the inverse, that's going to then take us back. So what we have to do is subtract 2 from that output value. So take away 2 takes us back, so the inverse here is just x minus 2. Forwards plus 2 minus subtract 2. So I've got a slightly trickier one. So let's look at the same starting set, so the same domain of 1, 2, and 3. But now I'm going to map into the codomain 1, 4, 9. So again, here this is going to be the square function. So f2 going forwards, f2 of x is going to be x squared. So 1 squared gives us 1, 2 squared 2, 2 squared 4, 3 squared gives us 9. So forwards we are squaring the values. Now we think about how can we go backwards, right? So if we are now at 9, how do we get back to the value it came from? So 9 came from 3. So how do we go from 9 back to 3? And we can say, well, the inverse then is going to be the square root. So it's the inverse operation of squaring. So we would say f2 inverse applied to x is the square root, which we write using this notation, the square root of x. And we can just check it makes sense with the others. If we have 4 and take its square root, we get 2. And if we have 1 and take the square root, we get 1. Now, if I slightly modify this function, and instead we think about f3, and this time, rather than having a finite, just 3 elements in our domain, let's suppose we go from the real numbers and we map into the real numbers. And we're going to have the same operation. So f3 of x is still going to be x squared. We're still going to square those numbers. So now if we want to go backwards, we've just seen that squaring a number going forwards means taking the square root when we go backwards. However, there is a subtle point here, because now if I want to do the inverse of the number 9, so with our previous example, we knew, having thought about the forwards direction, that 3 squared gave us 9. So when we go backwards, the 9 comes back and gives us 3, which is the square root. But I, on purpose, defined the inverse there to be the positive square root, because in this situation, there are actually going to be multiple numbers that map forwards to 9. So if I take the square root function here, I could actually get plus or minus 3. So let's just think about that for a moment. If I start at 3 and I square it, 3 times 3 gives me 9. So we map forwards into the codomain and we get 9. It's definitely a real number. But also, if I start at minus 3 and I square it, which means multiply it by itself, minus 3 multiplied by minus 3, the minuses cancel and you get 9 again. So those two numbers are going forwards to give us 9. So if I'm now at 9 in the output set, then I don't know if I've come from 3 or minus 3. So I have to put in a plus or minus to the situation. So really, F3 inverse here, we kind of want to say, right, well, it could be plus or minus root x, which is a true statement. Both of those square roots are valid, but we don't really like this. This is not a well-defined mathematical inverse, right? We preferred the other one when we knew exactly which input gave which output, and it allowed us to trace it back. So this is actually not a well-defined mathematical inverse. So this is giving us a clue here about when an inverse may or may not exist. So let's go and have a look at some more examples on the screen and see if we can derive those conditions we need for a function to have an inverse. So here is a function. It's actually the one we were just looking at. However, what I've done here is changed the domain. So we have the function plus 2. So we know this has a well-defined inverse. It's just subtract 2. But now we've got minus 1, 1, and 2. Add 2 to all of those numbers. Minus 1 plus 2 gives us 1. 1 plus 2 gives us 3. 2 plus 2 gives us 4. So we can represent this with a nice visual. So we've got here our domain x, which is this set minus 1, 1, and 2. And we can see that we've got our codomain y, 1, 3, and 4. And we can see that the numbers map nicely. So minus 1 goes to 1, 1 goes to 3, 2 goes to 4, shown by these 3 arrows. So we can see really clearly that if we wanted to go backwards, right, we just start at a point and we just draw backwards. So this has a nice, well-defined inverse. There's no confusion here. However, we have a slightly different function. So we're going to keep the same domain. So we're still mapping from minus 1, 1, and 2, and we're still mapping into the codomain of 1, 3, and 4. So these diagrams haven't changed. We still have x and y with 3 dots each. But if we now apply the squaring function, think about what happens. So minus 1 squared gives us 1. 1 squared gives us 1. And 2 squared gives us 4. So what we're seeing here, if we show this visually, is that before we had a single arrow going to each point between our two sets, but now we've got 2 arrows going to the same point. So that's minus 1 and 1, both mapping to 1 in the codomain. So that's a problem because we don't know which arrow to trace back. But also we have another issue here, because if I now start at this point, which here is going to be 3. So if I'm down here at 3, I can't go backwards. And that's also a problem. We don't want that to occur. So these two issues we're seeing with this second function, we need to have a way of defining, like to make sure they don't happen. So the first thing, where we have 2 of them going to the same point, so we want to say, how do we define it when that is not true? So we call that an injective function. So injective is the formal term. It's often referred to colloquially as one-to-one, which is a much nicer word, a much nicer way to remember what's happening, because it's saying one input gives you exactly one output. Sometimes you will also see the phrase F is an injection. So that is telling you it is injective, which again means one-to-one. So that's just saying one arrow is drawn from a point here going to a single point over there. There's no doubling up. So we want this to be true, right? We saw that with our example. That was a really nice property. So again, here, this is definitely an injective function. All of the arrows go from one single point to a single output. So that is a one-to-one mapping function. But over here, this is not one-to-one because those 2 go to the same point. So that is not one-to-one, which is bad. We don't like that if we're trying to define an inverse. OK, now the other property that we need, which we saw in that second example before, was surjectivity, or we say a function f is surjective, or a function f is a surjection, means that if each element in the codomain can be obtained, so every dot in my diagram has an arrow going into it, so every value can be reached, which technically means, in other words, the image of your function is the whole set. So the whole image, all of the points you can map to, gives you the entirety of the set. So we often refer to this as onto, again telling you it's onto the entire set, which is a nice way to remember what this property means. So if we go back to our diagrams, the first one, lovely and onto, we've got all 3 points can be reached with these arrows, but our second function, f2, is not onto, because what we've got here is we have a point which does not have an arrow going into it, so it's a non-onto function. It's not onto. So we actually want both of those things to be true, right? That's what we're seeing here. This is both of them to get that inverse. And so when both of them are true, when a function is both injective and surjective, it's both one-to-one, one arrow into each point, and it's surjective, meaning all of the points have an arrow. When both of those things are true, we say it's bijective, or we call f a bijection. And if f is a bijection, if f is bijective, that's when we can say it has an inverse function. So again, just to go over that, because it's a very, very important concept, the bijection, f being bijective, that's what we need for an inverse to exist. And what that means is it's both one-to-one and onto. So now we have 4 diagrams, and I want you to just take a moment and think about what properties each of these functions have. So some of them are one-to-one, some of them are onto. Remember, one-to-one injective, one arrow going into that point, and onto meaning all of the points can be reached, or surjective. So the first one is the example we've seen many times. This is our bijection. So this one is both one-to-one and it is onto. Now our second diagram, diagram B, now this is one-to-one. There is only ever one arrow going into those points. So it is one-to-one, but it's very clearly not onto, because this point cannot be reached. Now our third one, it's definitely onto. All of the points can be reached, but there's an issue in that 2 of them go to the same one. So that would be onto, but not one-to-one. So it is surjective, but not injective. And then finally, the example, again, we've seen a few times. This one is missing both of those properties we want, right? It's got 2 arrows going to the same point and a point that we can't get to. So only the first one, only function A here actually has a well-defined inverse. B, C, and D do not have well-defined inverses precisely because they are not bijections. So to summarize and to finish, let's now just go back to that original example we had before and see if we can fix it. So we were looking at the function f3 was the name I gave this. And we were saying that it was mapping initially, I'll write down the one we had before, from the reals to the reals. And we said that f3 of x was x squared. And the problem was that we wanted to take the square root, but we weren't sure. It could have come from the positive or the negative value, so it doesn't work. So what we have to do to fix this, to make sure it is both one-to-one and surjective. So if we want to make it one-to-one, then what we can do, and let's call this f4, so this one will be on-to-on, one-to-one. Okay. Should I just go from f4, or should I restart the surface bit?
Yeah, can you just restart the surface?
Yeah. Oh, I'm literally at the last bit. Right. Okay, so I'm just saying, right, so now we know how to define inverse. Let's go fix the example from earlier. Okay, and I'll just grab my clicker. On-to-on. I'm saying the words one-to-one and onto too many times. Okay. Go whenever? Okay, thank you. So now we have a formal, I had this on the screen. So now we have a formal definition of an inverse to summarize. And so now So now we have a formal definition of an inverse. Let's go back and fix that earlier example where we were unsure about how to define the square root. So heading back over to our surface, the function that we were looking at was f3 is going to map from the reals to the reals. And we said that f3 of x was given by x squared. So we are just squaring numbers. And we saw that the issue was when we tried to go backwards, for example, with 9, it had come from both plus and minus 3. So to make it one-to-one, to make sure we just have one element going to one element, we can actually restrict the map. So we can kind of like chop off part of that domain. And what I mean by that is we can define a new map, f4, which is going to go from the positive reals. So the notation for this is often to just put a little greater than or equal to 0 sign next to the r. So that just means the positive real numbers, and we map that into the reals. So now, when I have a value on my output, so now when I have 9, for example, if I now want to do the inverse of 9, then we take the square root. It could be plus or minus 3, but minus 3 is no longer in the domain. So that doesn't hold. So the only thing that it could have come from is 3. However, this still does not have a well-defined inverse. And the reason for that, and well done if you spotted this, is that the codomain, the output set, is still all of the real numbers. So if I now take a number like minus 9 and I try and go backwards, minus 9 is a real number, I cannot go backwards. Minus 9 does not have a square root in the positive real numbers. So that is a dot that does not have an arrow coming into it from our diagrams. So what we actually have to do, we're going to need an F5 to fully fix this. So F4 is one-to-one. F4 is injective, but it's not surjective. And remember, we need both of them. So our final bijection is F5 goes from the positive reals into the positive reals. And now finally, I can say we have a well-defined inverse where we take the number and we just take the positive square root. So to summarize, there's a lot more to inverse functions than perhaps you might think, but the core concept is we're just trying to go backwards. But to make sure it's well defined, we need to make sure that f, the original function, is first of all a bijection. counting functions allow us to compare the size of infinite sets. So an infinite set can be countable or uncountable, and there's a definition that tells us whether it is countable. Now that definition is related to the natural numbers. So we say an infinite set A is countable if each element of that set can be mapped to a natural number. And we want that map, we want that function to be a bijection. So that means it's sending one value, one input to one output, and all of them are covered. So in order to check if a set A is countable, what we need to do is find this bijection, find this function, find this counting function, sending the natural numbers into our set. And if we can do that, it's countable. Another helpful way of thinking about what this means is to say that the elements of the set A can be written in an ordered list. So that just means there's some kind of rule to that list which is going to be constructed through our function. So for example, A could be A1, A2, A3, dot, 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 up to AN, and then we continue, because of course it is an infinite set. But for example, we would be able to work out what the nth position is, right? There is a rule to it, it's not random. Now this is best demonstrated with some examples, as usual with these kinds of advanced topics. So given we have to use the natural numbers n, let's look at a subset of the natural numbers and let's focus on the even numbers. So if we head over to the surface, if I wanted to show that the even numbers are countable, then it would help to begin by writing out the set of even numbers. So A here is the set of even numbers, so they are numbers divisible by 2, so 2, 4, 6, 8, etc. And just for clarity, I am taking this to mean positive even numbers. So we want to show that this is a countable set. Now the order I've written the elements is exactly the order you would expect to write them. It's hopefully not a huge surprise if you've tried to do something like this before, that this is a countable set. There is an obvious order way to write out the even numbers. But let's just figure out what that bijection is so we can see how the definition works. So I like to do this by writing out here the natural numbers and kind of drawing a line between those two sets, very much like it's a function explicitly. So the natural numbers for this purpose, we start from 1. So we go the counting numbers 1, 2, 3, 4, dot, dot, dot in our set. And now we want a map, we want a function from n into the set A. So that means I need to send 1 to 2, I need to send 2 to 4, 3 to 6, 4 to 8. And of course, the value of n is telling us how to count them, right? It tells you the position of the even number in that list, which is why we say it's countable. So the function here, if we just think about this for a moment, would just be to say, well, if I input 1 and I get 2, I input 2, the second number is 4, the third number is 6, the fourth number is 8. We're just doubling the number. So our function, our counting function or our bijection is simply f of x equals 2x. That is a bijection. We are mapping all elements in n to all elements in A, all even numbers, so it's definitely onto and surjective, and we're going from one arrow goes into one number. So it's 1 to 1, it is injective, therefore altogether it's a bijection, and we can say that the set of even numbers is countable. Let's try one more. So we've got the counting numbers and we've looked at a subset of them in the form of the even numbers. So what if we go bigger than the natural numbers? What if we look at the integers, z or z, written like so? Now, I'm not going to write these out just yet because the order in which we should write them is not immediately obvious. Because in a way, if we think about like starting at 0, we just keep going negative. So we go -1, -2, -3, and we just go forever to that way. But also I could go back to 0 and go 1, 2, 3, 4, and keep going forever that way. So it's actually tricky to know like what is the order. We can't just write dot, 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 stuff in middle, dot, dot, dot. Right? That represents the integers, but it's not an ordered list. It's not a way to count the integers. So we have to be a little bit smarter. And the way we do this, and then I'll show you the bijection, is we start with 0, then we're going to add our positive number, and then what we want to do is actually add its negative counterpart. So we're kind of going 0, 1, and then we go its negative. So the next one's going to be 2, and then we go its negative. And then we go 3, and then we go its negative. So I've really here defined like a set of rules of how to order these numbers. But again, to fulfill our definition, we just need to make sure those set of rules can be written as a function that is a bijection. So once again, if we think about n and think about matching up those numbers, then what we're seeing here is we've got 1, we've got 2, 3, 4, maybe just go to 5. Carrying on. So if we draw the same arrows, then the first one has to go to 0. So we need a function that takes 1 to 0. We need to take 2 to 1. We take 3 to -1, 4 to 2, 5 to -2, and we carry on this way. So this is going to make sure that it's 1 to 1, and it's going to make sure that it's onto. But we need to define it. We need to have a way of expressing this using function notation, using algebra. So what we're going to actually do is create what's called a multi-step, or a, what's the word I'm looking for? I've literally forgotten the word. It's a piecewise function. Okay, so should I just go from, so what we're going to do?
Yeah, I think so.
Yeah, sorry, my mind went blank. I literally wrote it on my piece of paper. So what we're going to do, okay. So what we're going to do is create a multi-step or a piecewise function where, depending on the input, it's going to give us a different function is going to be applied. So I'll explain what I mean. So if we start with an even location in the natural numbers, so we're inputting 2, 4, 6, etc., then what we see is that they go to the positive numbers. So we're seeing there 2 is mapping to 1. We're seeing 4 is mapping to 2. So that all of the even natural numbers go to positive integers. And again, 2 going to 1, 4 going to 2, 6 would go to 3. There's a pattern, we're just halving it. So if the input is even, then we say f of x is just x over 2. That's what's happening. Now, if we have an odd position or an odd input, then we're going to the negative numbers and also 0. Let's just kind of write plus 0, just to make sure I'm not missing anything out. Now think about what's happening here. So 1 is going to 0, 3 is going to -1, 5 is going to -2. So there's some kind of halving happening, very similar to the evens, but we have to adjust it before we do the halving. So if you think about that for a moment, you'll hopefully realize that we need minus x minus 1 divided by 2. So again, we take our input. Let's suppose I'm at 3. So we start at 3. We take away 1. That gives us 2. We divide by 2, which gives us 1. And then we take the negative. And 3 is indeed mapping to -1. And just to really be clear on this, if we take 5, 5 minus 1 gives us 4. Divide by 2 is 2. Put the negative, we get -2. So this is going to be, it is indeed a bijection, as we can see from my drawing, and it is going to be, as I said, a piecewise function. So we would define this by saying, if the input is even, do this. If the input is odd, do this. And you can see how these things are very helpful and related to coding, programming, and computer science. Now I've got a final example. So I've talked about the natural numbers. Well, we use the natural numbers, I should say, to define how to count these sets. I then talked about the even numbers, and then we just looked at the integers. So we kind of got evens, naturals, integers. So next would be the rationals, those fractions where we have a number on the top and a number on the bottom. Now, to count the rationals, we actually do something a little bit different. It's a very, very clever proof, very clever method of showing how to count the rationals. And the way we do it is we list them in a table. So that at the moment that this is not a list. This is kind of a list across the first row, and each column is also its own individual list. So imagine it's like an infinitely long table. So the columns keep going and the rows keep going. And the way we've organized them is all of the numbers across the first row, we just count up. So we're just looking at the positive rationals. We go 1, 2, 3, 4, 5, and we carry on forever. And we divide them all by 1, writing it as a fraction, as a rational. The next line, we go 1, 2, 3, 4, 5, and we divide all of them by 2. The next one, 1, 2, 3, 4, 5, all divided by 3. So again, there is a way of constructing this table. We could define the rules of how we built this table. And this covers all positive rational numbers. We do need to also include the negatives, but we will get to that shortly. So once we have this infinite array or this infinite table, the clever part is how we now order the numbers. And we use, I like to call it a zigzag path. It's sometimes called a diagonal argument or a diagonal path through the numbers, or even diagonalization. But it's shown here through these arrows. So let's just carefully see which numbers appear in which order. So you begin in the top corner. So we have the number 1. We move across to get the number 2. We then go diagonally down to a half. So we add in a half. We then go down to a third. So we add in a third. And then we go diagonally up to 2 divided by 2. Now you'll notice 2 divided by 2 is just 1. And we've already included 1 in our list. So at this point, we are basically saying we're going to exclude any repeats. So we exclude this because it is a repeated element. So then we go on to the next element following the arrows, which is 3. So we add 3. Then we go across. It's going to give us 4. We go down following the arrows, 3 over 2. That's a new one. We go down to 2/3. That's another new number. We go down to a quarter. That's fine. We go down to a fifth. That's fine. And we get 2 divided by 4. That's a repeat. 2 divided by 4, if you simplify that fraction, is a half. We've already got a half. So we ignore that one. We then go to 3 over 3. That's another repeat. 3 over 3 is 1. Already counted it. 4 over 2. That's another repeat. That's a 2. Already counted it. And then we would go to 5. And then we carry on. So we would go across. And then we come back down. And then we go across. And you can continue to wind your way forever through this entire table. So it does give us a way of listing all positive rational numbers. Now, there is a final part required because we need the negatives. And the way we do this is very similar to how we counted the integers. So to recall, for the integers, we went 0, 1, and then it's negative, -1, and then 2, and then it's negative, -2. So we do the same thing here. So once we've got our positive list of the rationals, we will label these as Q1, Q2, Q3, Q4, label them as the rational numbers. And then what we do is we then just add in the negatives. So we go 0, then we go Q1, and then negative Q1, and then Q2, and then negative Q2, because every number here will have a negative counterpart. So what it would look like written out in full would be something like 0, 1, -1, 2, -2, a half, minus a half, and we would carry on through that list. It's obviously going to be a very, very long list, but it will follow this pattern, and it does provide an ordered list of all rational numbers, which shows that they are countable. So that's the natural numbers being used to define countability of an infinite set. We've then gone up to the integers, shown that they are also countable. Then we've just seen that the rationals are countable, which is introducing fractions. So next up, we would go to the real numbers. Now, it turns out the real numbers are uncountable, but I'm going to leave that one to the computer scientists. In this chapter, we've learned, God damn it, we've learned how to, okay. In this chapter, we've learned how to use variables and equations to translate real-world problems into solvable maths equations. Go again. Okay, in this lecture. In this chapter, we've learned how to use variables and equations to translate complex real-world problems into solvable maths. We've defined a function as a mapping from a domain into a codomain, and also seen the conditions under which an inverse function exists. Specifically, those conditions were when the function was a bijection, and we use that definition of bijection to allow us to count the size of an infinite set. We finally ended using the Pokemon catch function to catch Fampi the elephant. Next up, it would be great if we had a way to visualize these functions. Fortunately, we need graphs. Fortunately, that's where we're going. Hang on, give me 20 seconds, I'll go again. In this chapter, we've learned how to use variables and equations to translate complex real-world problems into solvable mathematics. We also learned how to define a function as a map from a set of inputs called the domain into a set of outputs called the codomain. We also learned how to define an inverse. We saw In this chapter, we've learned how to use variables and equations to translate complex real-world problems into solvable mathematics. We also defined a function as a mapping from a set of inputs or a domain into a set of outputs called the codomain. We saw that the inverse function doesn't always exist, and specifically the condition for the inverse to exist was that your function is a bijection. We then used the idea of a bijection to show that some infinite sets are in fact countable. And finally, we looked at the Pokemon function to help us to catch Fampi. Now we know everything there is to know about functions, it would be great if we could visualize them. For that, though, we're going to need graphs. Fortunately, that's where we're going in the next chapter.